Hello everybody, this is Dr. C. Pre-lecture today will focus on pH, something you're probably familiar with to some extent. So let's get started. This will take us into chapter 15 in the book. So we will be wrapping up chapter 14 very shortly and moving into chapter 15. So where do we get pH from? All right, and you probably know it's a measure of the acidity of a solution or the basicity of a solution, but where does the whole pH scale come from? And it comes from the equilibrium of water, okay? Because all the reactions we're going to look at are going to be aqueous, okay? So your solvent is water, all right? So say we have pure water, so we only have water. What happens in that solution of water? Well, for the most part, it stays as H2O, but some of it does react with itself, okay? And I'm going to write it down here and draw the structures. Now, you probably remember the Bronsted definition of acids and bases from last semester, okay? So a Bronsted acid is a hydrogen ion donor. Okay, so one of the water molecules donates an H plus to the other, producing hydronium and hydroxide. Okay, now what I'm going to try to get you to do rather than think of a Bronsted acid is think about a Lewis acid. And the reason why we're going to do this is really reactions are about electrons. They're not about protons. So even though we define an acid-base reaction quite often as proton transfer, I want you to start thinking about electrons. And this will be particularly important as you go on in chemistry. In organic chemistry, you will do a lot of things like I'm going to show you right now. So for example, the Lewis acid-base definition deals with one being an electron pair donor, the other being an electron pair acceptor. So let's look at this and let's use a different color arrow. Typically red is used for the arrows. This lone pair is going to come and form a bond to that hydrogen. Okay? And when it does so, this pair of electrons is going to come up on the oxygen. Okay? So this is giving a better picture of what's really going on. This H plus doesn't just jump off the one water and jump over to the other. No, it's really this water molecule saying, I'm going to take that hydrogen from you. Okay, I'm going to use my electrons to come over and grab that hydrogen away. And when we do that, we end up making, well, I'm not going to draw the correct structure here, but you get the idea. We get that guy. So the hydrogen has been stolen away by the one water molecule. The other water molecule has gained, he wasn't completely ripped off. The other water molecule got an extra pair of electrons. So this pair of electrons here goes up on the oxygen. Okay, so an extra pair of electrons. Now let's look at the charge. Okay, we show a positive charge here and a negative charge. That's easier to see when we say, oh, it's an H plus donor. But let's look at, oh my gosh, let's see if you remember this. Formal charge. Who remembers formal charge from last semester? So what we're going to do, God, I'm throwing a lot of stuff at you, but we're going to divide up the electrons in the bond. Do you remember doing this? And so for this oxygen, we're going to count 1, 2, 3, 1 in that bond, 1 in that bond, 4, 5. There's only 5 electrons assigned to that oxygen. Well, how many electrons does oxygen normally have? 6. So it has 1 less. So this oxygen has a +1 formal charge. H3O plus. There you go. If you looked at the hydrogens, they're all 0. So that has a +1 overall charge. What about this oxygen over here? How many does it have? 2, 4, 6, 7. There's 1 here in this bond. 7 electrons is 1 more. That's going to be a -1 formal charge. OH minus. Okay? So I've thrown a lot of stuff at you in terms of Bronsted acid definition, Lewis acid base definition. In effect, this is a Lewis base is an electron pair donor, and the acid is so this H plus is accepting electron pair acceptor. Okay, so we're going to start trying to think about more of electrons, but we'll still use all the time. Acid donates a hydrogen ion, base accepts the hydrogen ion. But we'll start drawing arrows to represent electrons moving in the reaction, because it's all about electrons. Chemical reactions involve electrons. Okay? All right, now let's write this out again. Well, here, let me just show you this. Sometimes molecular models help. In effect, this oxygen is coming over to steal that hydrogen. Those electrons are getting kicked up, and then we form OH minus and H3O plus. Okay, so there's a molecular model. Let's actually write out the reaction again and do some equilibrium. This is an equilibrium reaction. So again, let's write out H2O, liquid. Okay, now, initial, oh no, not another ice table. Pure liquids do not enter into the equilibrium constant expression. Our equilibrium constant expression, and it gets its own symbol for water, Kw. We only have to include the aqueous species. Pure liquids do not enter in. So we have a nice, simple equilibrium constant expression shown there. The Kw value for this equilibrium, and again, at 25 Celsius. K will be temperature dependent, but Kw at 25 Celsius is 1 times 10 to the negative 14th. Okay? Very, very, very small K, meaning that reactants are heavily favored. So not much of this reaction happens. Not too many water molecules react to produce our product. So I'm just going to put question marks here. Doesn't really matter how much water we start with as long as we have water present. The amount, its concentration doesn't really change. Initially, we would assume our products are both zero. We will produce a tiny amount of product. Coefficients are all 1. That's kind of nice. And at equilibrium, well, don't worry about the water because that doesn't go into the expression. We only have to worry about our products, and they're both X. That's really simple. This might be the simplest ice table when we go to solve for X that you've ever had in your entire life. Can you believe it? So we go back up to our Kw expression. Kw, only products. That's kind of nice. Okay, Kw is 1 times 10 to the negative 14th. Okay, at 25 Celsius. Remember, if we change the temperature, that value will change. But for almost all of these problems, we'll say 25 Celsius, about room temperature. We'll be focused on this, that temperature. X and X times X is X squared. Take the square root. Units. Square brackets, what do they mean? Molarity. All right, so that shows you that this reaction, this what's called the auto-ionization of water, doesn't really happen to any great extent. We get a very, very small amount of product. But this product, guess what it equals? It equals hydronium. What else does it equal? Hydroxide. Okay, so what you see is in a pure water solution, H3O plus, hydronium, equals hydroxide. That's a neutral solution. If those two things are equal, hydronium, H3O plus, and hydroxide, the solution is neutral. All right, now, lots of stuff, but you'll notice that's a really small number. We don't want to really work with really small numbers, so what do? We devise the pH scale. So as you read here, H plus, now a lot of times we will write H3O plus shorthand as H plus, okay? But H3O plus is a better representation of how that species really exists in water, okay? But you'll see H plus as shorthand. Those are very small numbers as you saw for a pure water solution. Therefore, we typically take the negative log of that. So if we had pure water where H3O plus is equal to 1 times 10 to the negative 7th molar, all right, we would then say pH is the negative log of 1 times 10 to the negative 7th molar. Make sure you notice this is not natural log, this is log base 10. Okay, so find your log key on your calculator. Take the log of 1 times 10 to the negative 7th. And when you do that, you're going to get negative 7. It's just going to equal that exponent since this is just a 1 in front. And then negative of negative 7, pH is equal to 7. And I know you've seen that number before. That is a neutral pH. When H3O plus, again at 25 Celsius, equals OH minus, that's neutral. So at any time, even if we're at a different temperature, if H3O plus equals hydroxide, solution is neutral. Those concentrations at 25 Celsius happen to be 1 times 10 to the negative 7th molar. And when we take the pH, pH is 7. That's a neutral pH. Okay? What does it mean for something to be acidic? Acids produce hydronium. That's another definition of an acid. So compared to a neutral solution, hydronium goes up. Okay, so it's going to be greater than 1 times 10 to the negative 7th. Hydroxide thereby would go down. It's going to be less than 1 times 10 to the negative 7th. So I want you to start thinking about it. In an acidic solution, we still have hydroxide, but we just have more hydronium. More hydronium, less hydroxide. Now, as a calculation, let's say acidic. Hydronium has gone up. We've added acid. Our hydronium is now 1 times 10 to the negative 2nd molar. Okay? If we take the negative log of that, okay, we're going to get negative of a negative 2. So we're going to get a negative 2 when we take that log, change the sign, pH is 2. So if hydronium goes up, as it will in an acidic solution, our pH goes down because it's a negative log scale. Okay? So low pHs, pH is less than 7. I'm sorry, I'm just drawing circles everywhere here, aren't I? pH less than 7. And that didn't change my color. Okay? Acidic. Right? Conversely, in a basic solution, all right, bases produce hydroxide. Okay? So your hydroxide is going to go up. If your hydroxide goes up, hydronium goes down. Okay? Because you know why that happens? There's our equilibrium. If hydroxide in a basic solution is going to go up, hydronium has to go down to equal that same constant. Okay? So neutral solution, they're equal. Acids produce H3O plus. H3O plus goes up, hydroxide goes down to equal that same constant. Conversely, as we saw in a basic solutions produce hydroxide. Hydroxide goes up, and I'm moving my thumb up in the air, as you can see, and hydronium goes down to equal that same constant. But even in a basic solution, we're still going to have hydronium in a basic solution. It's just going to be less than our hydroxide concentration. Okay. I was going to talk about POH, but I think I'm going to leave it for there because I think I'm in about 14 minutes. Now, in the pre-lecture quiz, you'll definitely have some questions with KW. You might be asked to, given KW and hydronium, solve for hydroxide. You'll probably have a question that just has to do with what's a neutral pH or what's a neutral hydronium, what's an acidic hydronium. That gets into the, 1 times 10 to the negative 7th. Okay, at 25 Celsius, they're equal. Acidic, you have more hydronium. Basic solution, you have less hydronium, more hydroxide. Okay? And then I might have some very simple ones where you're asked to calculate pH using the pH equation. pH is equal to negative log of hydronium. So once you have your hydronium concentration, just plug it in there, solve for pH. Okay? So I think the questions in the pre-lecture quiz will be pretty straightforward. KW, pH, things like that. Okay, that's all I want to do for now. We will pick this up in class, and I think you probably have at least some of the fundamentals of pH down. We're going to look at it in probably a little bit more detail than you have in the past. Okay, see you soon.